one thing that you look at, one thing about the answer here is that, right? Wait, no, they're actually in proper order. So, a lot of the time, right, actually, some of the answer here, you need to look them in the reverse way. Because what I mean is that, like, they know what they need to look for. So they just look for everything that they need, then the answer at the end. If you look at it the other way around, probably it might make more sense. But never mind, let's see. Maybe we can discuss some of the questions. So there's no particular question that you want me to discuss, is it?
Yes, sir. I think so.
Then I will choose. Alright, okay. 1, 2 are pretty straightforward, so I will skip. Now, maybe we have a quick look at problem 3, a very quick one. So a fixed mass of an ideal gas is heated from 50 to 80 degrees Celsius. So you have an ideal gas that you heat up from 50 to 80 degrees Celsius. So the change in temperature is 30 degrees Celsius. Now, but you have two situations here. One, this mass is being heated up under constant volume. The other one is under constant pressure. For which case will energy required be greater and why? So which one do you think is the case here?
Fixed mass.
Okay, so for this question, now the way that you can look at it, right? Okay, so one way is very straightforward, is that always remember this: when you're dealing with ideal gas, I always mention there are two methods, right? Either you look at the table or you can use calculation directly. By calculation, I mean Cp delta T or Cv delta T. So now, in both situations, so in A, what we get is based on Cv delta T, right? If you just look at it this way now. So like the most straightforward way that you can look at this is Q is equal to Cv delta T. While for B, what we look at is Q equals to Cp delta T, because this is under constant pressure, the other one under constant volume. And this will equate to change in U. This is change in H, because I mean if you want to M lah, because I write capital letter. Right, so this was what I mean. So for ideal gas, one of the things that you need to straight away think of is actually this. But no worries here, because in your future chapter when we go to power cycle also, we will come back to this thing. So by that time, hopefully you are like, it's automatic lah. You should know that that is one of the methods. Alright, so now if you just look at these two, the most straightforward way to look at it. So like now makes sense, right? So one is under constant volume, the other one constant pressure. So if you just look at this mathematically, if you just look at the table that you have, Cv value is forever higher than Cv value lah. So this mathematically point of view, okay? Cv value is always higher than Cv value, so meaning that B will always require a higher energy. But of course, if we look at it in more theory term, the real reason here would be this. We also know that enthalpy is U plus PV, right? So here we have this extra term here. And in this case, let's say if we are looking at a closed system, right? Case A will be a rigid tank, let's say. While case B, under constant pressure, will be a piston cylinder device. So in case A, if you are providing heat to heat it up from 50 to 80 degrees Celsius, so all you are doing is basically heating it up, changing the temperature. But in case B, if you are providing heat, not only you are changing the temperature, you are also trying to overcome the boundary work that is being done because it will expand. So that's why in case B you will require a higher energy for you to achieve the same temperature change. This case. So yeah. So enthalpy always have a higher energy compared to internal energy because you have the additional PV there. So in closed system the PV is boundary work. In open system that PV is flow energy. Okay, so this is just something a bit more theory here. Okay, then we move on to, let's see. The rest I feel like we jump straight to something a bit harder, but this is still, so we focus on gas here. Now you can see that here you have some question. Maybe we look at it. Problem 4 first, I won't discuss, but so like problem 4 is about liquid water and vapor. So meaning you are dealing with H2O. Your only way to solve this is table. Okay, A5 to A4 to A6, I think. So when you see water, this is always your solution. So usually, at least to me, water is easier to solve than gas because you have less steps. But that will require you to understand how to read the table. Right? So that one you need to work harder on that. Now, we look at problem 6 here. Okay, problem 6 here we have a piston cylinder device, but this question is about air. So let's take this. Wait, I think. Oh yeah, correct. Enough. Oh, okay. Let's go down. Problem what again? 6. Okay, so this question, you are given a piston cylinder device. With spring. Okay, so the question says spring. Okay, so always remember when you are solving thermal question, so first thing you need to identify whether you are dealing with closed system or open system. But again, obviously in class this is very obvious because they are split into chapters. But you always need to identify which system you are dealing with. So this one you are dealing with closed system. Alright? Okay, now then the next thing you need to do, of course, to look at what substance you have, which is air or water, those will define who you dedicate what you that will determine what you need, how you want to solve the question. Oh, by the way, next time it's more polite if you want to record, you ask the lecturer first. Because technically speaking, you are recording the person. You need permission. Like in my case, I mean, I'm not in there, so it's still okay. Yeah. Just reminding you. More polite than there also, I know this. Alright, okay. So two things. So closed system and what? So those things later we will see how they factor in. But for now, let's look at what information are given to you first. So you are given volume. So initial volume is 0.03 meter cube of air contained in a spring-loaded piston cylinder device shown in the figure. The spring constant is 875 Newton per meter. So you have K 875 Newton per meter. And the piston diameter is 25 cm. So this is a K, you have diameter here. So initially, so you are told that when no force is exerted by the spring on the piston, so this is the initial state. So initial state P1 is 2050 kilopascal, T1 is 240 degrees Celsius. And the device is now cooled, so you are taking heat away until the volume is 1/2 of its original. So we know that V2 is half of V1. which is 0.015 lah. Determine the change in the specific internal energy and enthalpy of the air. Okay, so this is where what I said just now will factor in here. So closed system, open system. This is a closed system. So closed system, you always start with the energy equation, which is Q minus W equals to delta U, right? And what do I want to say? Okay, so for this question, let's say if you look at the answer, then it won't make sense. Because this question will leave this entire thing up to the end. Because like I said, the question itself knows what it is looking for. But for you, you don't know yet. That's why you should start with this kind of equation first. So this is a guess. Again, ideal guess, the question should tell you which method you use. But the method thing, we will only talk about them in chapter 8. Okay, so in this case, you are looking for delta U, which is mCV delta T. So mCV T2 minus T1 lah. Of course, the question also asks for specific enthalpy. That one we can leave it later because enthalpy basically you are just looking for mCp delta T, which it's the same thing lah. CV, Cp based on the air, based on the table. Doesn't matter. So in this case, we can still identify what we need here. Okay. To be fair, for this question, you don't really need to write Q minus W also because the question just specifically says specific internal energy or enthalpy. So either way, meaning in this case, actually this one is not too important, but we can write it out just for you to look at this question lah. So for this question, let's say, so we have Q out. So Q out should be negative. Then you will have work in, so negative work in. So again, like I said, this question actually, let me see this one. Does it matter? Probably not very important, but we can just write it out because it might be useful for other questions also. So in the end, this will be the general equation that you have. Alright, so now generally speaking, whether you are dealing with air or water, this case is still, the method here is still the same. We are just not using MC delta T anymore. If you are dealing with water, just delta U, that's all. Then you get the U value from the table. Okay, so here, but here again, like I said, the work in and Q out probably not too important here because you don't really need them in this case. So in this case, let's look at this question. This is unknown. This is unknown. That's why I said you don't really need them. I mean, you can find them, but for this particular question, we can find, but doesn't matter here. So we look at the right hand side first. CV you can get from table, so that one we don't care. You need mass, but the question actually say specific internal energy, meaning this one you don't need. We change them to the small letter version. So left with this. So meaning you need T2. You need to find a T2. So T2 is the main thing that you want to find here. Actually, this question, the answer here very confusing. You find a lot of extra things. Alright, now, so how do we find T2? This is the main question for this question. For this one. Right, that will be the one that you need to solve. So how do we find T2 in this case? Initial state, we kind of have everything. We have T2, we have V2, we have P1, we have V1, we have T1. Okay, you have everything. Final state, you actually only know this. Right, then, so how can we make use of all these things to help you to find T2? So one thing that you need to remember here. So now, actually that's the answer. So when you deal with water, then actually it's very easy because like in this case, of course the value won't be the same lah because it won't be applicable. Like in this case, actually, if you do water, very easy because you have pressure, you have temperature, you can kind of find the U value and stuff. Okay, so here, for when you're dealing with ideal gas, whenever you see PV and T, you need to remember that you have ideal gas law. Okay, so for this one, actually, even if we don't want, even if the question doesn't ask for specific internal energy, let's say it asks for internal energy, you can still find mass in this case because of ideal gas law. But here we don't need the mass, so you can actually find it through just this one because the rest are all constant, right? M is constant, R is constant, so you can just straight away do this. So here you have everything, but of course we are still missing something. What are we missing here? We are missing P2. Right, so P1, V1, T1 we have everything. B2 we need to find T2. So in order to find T2, you need P2. So the question here is how to find P2. Then, so we are adding more questions. So now we need to find P2. So one thing that you know about this particular thing is, so initially P1 was when the spring is not doing any work, and then but after the cooling, the spring is cooling actually. Okay, so let's draw this thing a bit. So initial case, let's draw a free body diagram. So initial case, spring is not doing anything. So meaning here this will be, so you will have a force from atmosphere. You will also have the force from, or rather we call it weight of the piston. These are the only thing that you have. And then the one resisting it is F1. I intentionally don't write pressure because like I mentioned in the first class, there's no such thing as conservation of pressure, okay? There's only force, but in this case it's the same thing because they're acting on the same area. So this one makes sense, right? Initially, this is all you have. So F1 comes from P1. The pressure itself is the one that is resisting. So after the cooling effect, this still remains. This also still remains. And this, of course, this will be a new pressure, right? The new force. But the spring, so which direction will the force of the spring go? Up. Because your piston moves down, spring will always resist the movement of the object. So the spring will pull it back up. So when you write this thing, so when you write this equation, plus work piston equals to, so the first one is actually equals to F1. F1 will be P1 A1, right? And then the second one will be FATM plus work piston equals to F spring plus F2 A2. Sorry, A still A lah actually, doesn't need A1. Okay, make sense? So even though we don't know this thing, technically we don't need them. Right? Because this is simply P1A equals to F spring. How do you calculate force from the spring? Kx. Okay, so this will be the change in the length of the spring. K is given, but you need to be careful of the unit here because this is now of Newton per meter. We always calculate your pressure is all in kilopascal, so be careful about that. Then here, this one is P. Sorry, not F2. It's a P2. So then P2 over A. So from here you have P1 value, you need to find, so P2 equals to P1 minus Kx over A. So X you can find as well because you know the initial volume. You know the final volume basically minus V2 equals to delta V, then delta V will be equals to X multiplied by area. So from here you can calculate the X. Then you can get P2. So once you get P2, then you can get T2, then you can solve this equation. So then you can solve the question, then you can get internal energy. Okay, so these are the looking. Make sense? So maybe let's say here I add an additional question here. What is Q out? Then you can solve this, right? Can you solve this? Because your boundary work is actually simply the spring work. The spring, so boundary work is simply the spring work. So in this case, you can sub in the work done by the spring, which is in this case, then it will become kx squared. So you can find Q out. Now, if you are asked to draw this graph, right? Now, this graph, of course, since we are dealing with air, is very easy. So let's say if you're asked to draw PV diagram. Okay, when you have spring, the graph itself is actually very easy to draw because it is just a linear line. You just need to see. So like in this case, initial V is higher, is a larger value. So V1. Then after that, so here you should find that P2 is smaller than P1 as well, which is very obvious there because you can see that P2 definitely is a smaller value based on this equation here. So it is just a straight line here, V2. If there is no spring, in this case, assume there is no spring. Of course, if there is no spring, you don't have enough information to find P as well. But let's say if there's no spring in this case, right, then this graph will look something like this. So it will always be a curve and a positive curve. So regardless whether you are dealing with expansion or compression, the curve, it will always be a positive curve, a smiley curve, the change. So only when you have spring, then it becomes a linear line. Wait, sorry, just now I think I said something a bit wrong, which is about the boundary work. The boundary work in this case will actually be this one, not just Kx. So area under the curve, this whole thing. So you can find boundary work through area under the PV diagram. I forgot about the initial, right? Okay, so additional question, like I said, so boundary work in this case would be, let's say if we just want a small boundary work, this will be actually P small v, or if the capital letter one, then it is capital V, so P capital V. In this case, then this is the area under PV diagram, which is one over two V1 minus V2, then P1 plus P2. Okay, area under the graph. This is the for the trapezium. If you don't, you cannot get it, then just split into two, one rectangle, one triangle, then add them up. Okay, so yeah, this is actually one thing very important also. You will see in some of the class here as well. Whenever you have a spring, right, this it will be the easiest for you to find out the boundary work as well, because then you can just draw the graph, then you just, based on the graph, PV diagram, then you can find the boundary work just from there. Then you don't need to worry, think too much about it. If there's no spring, then using area under the graph will be a bit tricky because you will get a curve. Then you don't know how to find. Then the area under the graph is harder to find. And like I said, I will ask you to do integration, so those cases won't happen. Then you will need other method to find. With spring, then yes, you just need area under the graph. I think for closed system, I will stop here, or we jump straight to open system, because open system here has more complicated question, I think. Actually, what was the open system question that I asked just now in test?
Turbine.
Turbine. Oh. Then we don't talk about turbine. Actually, open system is easier than closed system, at least to me. So here, maybe we look at, we look at problem 11. Maybe. So once again, we are dealing with air here. For some reason, I keep choosing question with air. So you have a nozzle, P1 is 600 kilopascal, T1 is 500 Kelvin. Enters an adiabatic nozzle, so there is no change in Q here. Has an inlet to exit ratio of 2 to 1. So A1 to A2 is 2 to 1. With a velocity of 120 meters per second and exit with velocity of 380 meters per second. So A determine the exit temperature and B the exit pressure. So open system. So here we are dealing with open system. Again, very straightforward. For open system, first thing you do is you write this entire thing. Space. Okay, so for a nozzle, we don't really have any change in work. Since we are told that this is an adiabatic nozzle, this one you can solve as well. Of course, if the question says there is energy loss or gain, then you follow heat loss or heat gain. But otherwise, just cancel them off since it says adiabatic. Potential energy, 99% of the time we cancel this off. Mostly you won't get any example that will require this. But again, question dependent, so you read the question. So this is a nozzle. Obviously, you cannot cancel off the kinetic energy term, no matter how insignificant it is, because that is the major purpose of it. So in this case, you can simplify this equation to m dot h1 plus v1 square over 2 equals to m dot h2 plus v2 square over 2. So from here, mass flow rate can cancel off. Then you are left with h1 and h2. So if we move things around, then you get v2 square minus v1 square minus v2 square over 2. h2 minus h1, which also equals to, again, this is an open system. This is ideal gas. So Cp T2 minus T1. Okay, so from here, then you can determine exit temperature, which is T2, right? That is what the question asked for. So question asked for P2 as well as T2. So from here, you have everything. V1, you have V2. Cp, you can get from the table. Usually, we just assume 300 Kelvin if the question doesn't really ask for too much. Then you have T1 as well. Then you can find T2 in this case. Or you, okay, so the only thing that you need to pay attention to here is this. This will give you kilojoule per kg. This will give you joule per kg. So be careful about the 1000 here. So this is one thing that you must be careful of, or else your value will be very ridiculous. So one thing for you to remember this is this. Kinetic energy usually doesn't have very significant effect on the overall energy change. So yeah, if you notice that it changes your value back too much, then something is wrong. Okay, potential energy, then maybe yes, you might have a lot of effect, but velocity, kinetic energy, no, not much. So in this case, then there is this. So this is one thing that you need to be careful of. All right, B asks for exit pressure. Then how do you find exit pressure? What can you do to find the exit pressure? No, in this case, it's not PV equals to MRT anymore. Even though I say you have P, you have B, you have T, you can use Heidegger's law. But this case, no. Yes, this case is mass flow rate. Okay, so always remember as well, this as well. Mass and mass flow rate are constant in our case. This will be the opposite. Actually, not really opposite. It's kind of the so what we do here is kind of the opposite of in fluid. Okay, so in fluid we always deal with density. We treat density as mass, because the volume is always kind of constant. In our case, it's the other way around. Our volume is not constant because it is constant. We are dealing with mostly dealing with compressible flow for us. In a way because our specific volume always change. So in our case, we always focus with volume. Our mass is always constant. So in this case, the one that you are more familiar with will be rho A V, right? That is the mass flow rate. So one, like I said, in our case is always compressible instead of incompressible. So we don't have density. We don't have density, but we do have the actually what do we have? We actually don't have anything at all. That means specific volume and density the same thing, right? But how do you find specific volume?
Using the property table.
This A. Ideal gas don't have. Yeah. Ideal gas don't. Okay, so for again this one later only you will learn. I mean you have learned it, but if you actually flip to the ideal gas table, right, there is actually no specific volume for gas. Because for gas it can be at any specific volume at a specific temperature. It is something that will change. Like it can be at any pressure, any volume. So the table won't give you that information. So actually then you come back to ideal gas equation. Then in this case. Of course, like in our case, sometimes we write it this way but then doesn't matter you should know that these two things are the same thing. Okay, the specific volume. So in our case, we actually go back to ideal gas equation. So PV equals to RT. So 1, 1, 1. And P2V2 equals to RT2. So same thing, right? So from here, if you move everything, then this becomes P2 RT2. Sorry, 1. So A1 B1 equals to P2 RT2 A2 B2. So what you want is P2, you move everything around. You will get what we will get. T1, T2 over T1, A1 over A2, V, so this V is the velocity, V2. R cancel off. So a reminder, T change to convert to Kelvin. All this while I didn't mention because all the previous examples we were dealing with difference, T2 minus T1. So when it's differences, Kelvin over degree Celsius doesn't matter. But when it comes to division, then yes. So always remember to convert to Kelvin. Okay, so this way then you can solve this and get P2 for this question. Okay, so we have enough looking at air. Let's go to something. Let's go to water. Open system. Now, I try to discuss two more. One is shorter, but just to show you something. Okay. Okay, now problem three actually is a very simple question. The diagram here very complicated because we are showing you what's the internal of a valve look like. But in actual, the question that we want is just that. So a well-insulated valve, let me zoom in a bit, is used to throttle steam from 8 megapascal and 350 degrees Celsius to 2 megapascal. Determine the final temperature of the steam. Okay, the diagram is actually not necessary for this case. Okay, so we have a well-insulated valve. Again, you see well-insulated valve meaning there is no change in Q. Right? It's used to throttle steam from 8 megapascal to 350 degrees Celsius to 2 megapascal. So we know that initially we have 8 megapascal, 350 degrees Celsius, and final we have 2 megapascal. You need to determine final temperature. So you do the same thing. Q in plus work in plus m dot. I'll just write H1 this time because V1 and the I write the whole thing. H1 plus V1 squared over 2 plus GZ1 equals to Q out plus work out plus m dot H2 plus V2 squared over 2 plus GZ2. Right? So same thing, insulated, so we cancel off Q. The question is about a valve. So this is simply just a valve. So in other words, this is a throttling valve lah. Like if you have done your lab, then this is the expansion valve that you are looking at. Okay? So theoretically speaking, when you look at this question, when you look at the valve, okay, this one is not theoretical, this one memang is the case. There shouldn't be any work in a valve because it's just simply a valve. A valve is just a valve. We use it to throttle the flow. Basically, you use it to change the flow. But again, unlike in fluid, when the flow, when you have throttling valve, you have pump, you have turbine, what happens is that the pressure change. Velocity may change or may not change because of the change in specific volume or density. So when those things change, right, velocity actually sometimes might change, might not change. But in most cases, even if they change, it is not very significant. So if the question doesn't tell you there's a change in velocity, you can just cancel it off as well. So GZ also cancel off. So ultimately, you will see that this one comes down to this very weird thing, which is, and then mass flow we can cancel off. Actually, we are left with this. So very weird, right? So what are we looking for? Since enthalpy are the same.
U plus PV. U plus PV.
That was what I showed in the lecture notes, right? Actually, you don't need also in this case.
Oh wait. MCP.
That one is for air. Yeah, they need water here.
Oh, okay.
Okay, so now this is also the same case for those who have done labs. Okay, where from your stage 3 to stage 4 is just straight line because we say enthalpy doesn't change. Now, enthalpy doesn't change, doesn't mean that properties don't change. Okay, so properties depends on other things as well. So initially you see, so what you can do here is actually just this. So U plus PV equals U plus V, that one, okay, makes sense. But since we are dealing with here, we actually, water here, we actually don't need that. You can see here. So we know that T1 is this. You know that T1 is 350 degrees Celsius. You can actually check this at the properties table, right? To obtain what is H1. Based on this, so this temperature and this pressure, actually I'm not very sure what state this is. Let's see. Okay, maybe we demo a bit lah. Hi. Okay, let's go to the table. We check for 8 megapascal or 350 degrees Celsius. So like I said, either one is fine since you are given both, but you shouldn't expect it to be at a saturated state because you have both of them. Because if they are saturated state, then you are screwed. You cannot find anything. Okay, so we look at 350. So at 350, the saturated pressure is 16,000, which is 16 megapascal. So the 16,529 is the saturated pressure. So which means that in this case, what state do we have here? Okay, I mean, we look at it the other way around. Let's go to 8 megapascal. Okay, so 8 megapascal, the saturated temperature is 295. What you have is 350. So it is superheated vapor. Compressed liquid, remember, pressure should be higher. That's why you call compressed liquid. You can think of it that way. Okay, so at 8,000 kilopascal, saturated temperature is 295, meaning that is the boiling point. The temperature that you have is 350, so it is higher than that. So this is a superheated liquid. Oh, sorry, superheated liquid is the wrong thing. Superheated water. So now we go to 8 megapascal table. You look at 350 degrees Celsius. So the 350 degrees Celsius is on the third row, 8 megapascal. So third row 1, 2, 3. This row what you are looking for is this row. Okay, so enthalpy, we want enthalpy 2988.1. So here H1 is 2988.1. Okay, this is superheated water, H2O. Okay, so now then we bring back to this. We know H2 equals H1, right? So why do I say we don't need to go to U plus PV? Because we are actually looking only for the properties. By that, I mean, we know that T2 is 2 megapascal. So from here, we have two properties, right? We have two independent properties, meaning you have enough information for you to find out what is T2. So the enthalpy is the same, but because they are at different states, so they won't have same temperature or pressure. Even though enthalpy is still the same, energy remains unchanged, but other things have changed. So from here, then you do the same thing, but reverse. This time you check for 2 megapascal, but you look for H equals to 2988.1. Okay, so once again you go back to the saturated table. You look for 2 megapascal. So 2 megapascal is here. (2988.1) for enthalpy. So now we compare with Hg. Okay, this Hg value is 2798.3. It is lower than 298.1, right? If it is lower, it means that this is lower than 298. So if the so think of it this way: if the water has more energy than your saturated vapor, then meaning it is superheated water because they have more energy. That's why the molecule is moving more rapidly. That's why more energy, right? So you go back. So now we go back down again. So technically speaking, you can actually check at 2 megapascal here as well, because the first row actually gives you the saturated vapor value lah. But this one a bit confusing. So my advice is always go back to the saturated table to check. So 2 megapascal, we look for 2988.1. So in this case, we don't have 298.1 here. We only have these two. So you need to interpolate between them, meaning between these two temperature. So the temperature here should be between the 250 and 300 lah. The answer here is 285. Okay, so if you interpolate this one, you try, you should get this value. Okay, so this one I will leave it for you to try. So in essence, again, enthalpy is the same, doesn't matter. Okay, because there are still changes in all these things. So ultimately, you will still get different answer there. It's just the value is the same as well. So the whole demo is about you trying to find the connections between here basically. Like what's the first one, what's the second one, what are their connection. So in this case, their connection is the initial enthalpy equals to the final. So then you can, and then you will always need to find out what are the two independent properties for each of the state. Then you can find the rest. Okay, so for this question, I will skip. So we have 8 more minutes. Let's quickly look at the last question, which is problem 14. This one is more interesting, that's why I want to look at this. Actually, what did my answer give? Okay, this question, right, don't follow my answer, because my answer is something that I don't agree with. But yeah. Alright, only on one part. The main method is still the same. Okay, so we look at this one. Steam is to be condensed in the condenser of a steam power plant at a temperature of 50 degrees Celsius with cooling water from a nearby lake, which enters the tubes of the condenser at 18 degrees Celsius at a rate of 101 kilogram per second and leaves at 27 degrees Celsius. You need to determine the rate of condensation of the steam in the condenser. Okay, so once again, this is an open system. You need to figure out what you need to do here first. Okay, so this is a heat exchanger. Okay, so remember when I mentioned something whereby I said that heat exchanger, you can actually look at them individually, meaning you look at only this one, or you look at it as a whole. So here we look at it as a whole first. So if we look at this whole thing as a whole, then there shouldn't be any heat. Let's see, this one, this is 2, this is 3, let's call it this 4. So this time I won't write the whole thing because we are short on time. But essentially what you are left with will be m dot h1 plus h3 equals to m dot h2 plus h4. So this is the outlet, this is the inlet. My answer here actually just split them into 2, that's all, it's the same thing. Meaning Q in, so Q in equals to condensation. Q out from is H2 minus H1, Q in is H4 minus H3. Okay, keep everything as positive. Okay, now let me think how to say, how do we talk about this? Okay, so the rate of condensation of the water, meaning what you are looking for is, oh wait, sorry, the way that I write here is actually wrong. Let me change a bit here. Okay, so H1 is actually for the steam, right? Let's call it steam. This is for the cooling water, so this H3, they have different rates. So if you move them around, then you get H1 minus H2, m dot Cw, H3, H4 minus H3. Okay, now I will settle the one on the right first. So mass flow rate of the cooling water, you have the answer, right? So mass flow rate of the cooling water, you have the answer. But here, now, in my answer here, H4 minus H3, they use Cp delta T. The Cp is just 4,000 something, I think. Yeah, 4.18 for water, which is something that you learned in high school. But for me, I usually don't agree with this method because like I said, don't confuse yourself, water don't use Cp delta T. So in this case, since it's just a cooling water, how do you find the answer? H4 and H3 will be, so water is compressed liquid, right? So this will be HF at 18 degrees Celsius. This will be HF at 27 degrees Celsius. Because you treat them as compressed liquid. Okay? Just use this method. This method will be more accurate than using Cp delta T. Meaning compressed liquid, at this temperature, you can treat them as saturated liquid. So use the saturated liquid value for that, for the H. Okay, now issue here is the left side. You need to find out H1 and H2. But what you have here is only 50 degrees Celsius. You don't know anything else, right? So what do we do? So the tricky part here is there's one small assumption that you need to make, but don't really need also lah. You see, you supply steam in, right? Meaning the one that you supply should be fully gas. In a way lah, vapor. Because you are supplying steam. You are not going to put in mixture, right? And then it got condensed, then what comes out is liquid. So meaning this is a full, and then temperature doesn't change. Meaning this is a full condensation process. So in a way, what I'm trying to say here is it goes in as a saturated vapor. And then it comes out as saturated liquid. Because temperature doesn't change. If temperature change, then you cannot make that same assumption. Because then the one that comes in can be superheated vapor. But if temperature doesn't change, meaning it goes through a proper full condensation process without any temperature change. Yeah. So it means that this is actually a saturated vapor. And it comes out as saturated liquid. Which is why there is no temperature change. 50 degrees Celsius, then it maintains at 50 degrees Celsius. So, which means for this, you can simply use HFG at 50 degrees Celsius. Or if you find this hard to understand, then you just write Hg minus HF lah, then at 50 degrees Celsius. Same thing. So you solve this, then you can get the mass flow rate for the steam. Does it make sense to you? Like, it goes in as saturated vapor, comes out as saturated liquid. This example is intentionally tricky lah for that part. Like it requires you to understand what is happening over there. So any question? You have 1 more minute before we ask the class to other people.
Yeah.
So the attendance code is what?
715669. Time pass
我
already.
腰不是他的。